Most spreadsheets are treated as static digital ledger books, simple containers for manual data entry. Relying on this environment as a basic calculator misses the sophisticated architecture governing how that data interacts. The grid serves as the foundation for a multi-layered computational ecosystem. Beneath the visible cells lies a dynamic computational core that operates through strict logical hierarchies. A second layer utilizes algorithmic automation to sanitize and extract data. The final layer consists of isolated memory architectures designed to aggregate massive datasets without straining the system's processing core. To understand this system, we must build a mental model of these layers, from the geometry of a cell to the mechanics of memory caching. Mastering these structural mechanics allows for the engineering of scalable business intelligence systems rather than fragile manual trackers. The architecture of the computational engine begins at the very most granular level, a single formula connecting two individual cells. By default, the grid operates through relative spatial geometry rather than fixed coordinates. Instead of a specific address, it records a physical direction vector. This fails against a constant variable. Copied down, the vector slips off into an empty row, breaking the calculation. Absolute referencing provides a rigid structural anchor, permanently tethering the vector to that exact coordinate. Two-dimensional modeling requires an even more precise application of this logic, the mixed reference. Locking a column allows for rigid horizontal lookups, while the row remains free to move vertically. Conversely, locking the row anchors a header, allowing formulas to expand horizontally across the entire grid. Combining these two locks allows a single formula to populate a 100-cell grid symmetrically. Using mixed references minimizes manual formula adjustments that often lead to calculation errors in large datasets. Controlling this spatial geometry is the baseline requirement for constructing scalable analytical models. Moving to the internal engine reveals a strict sequence used to parse every single formula. Evaluation follows a precise hierarchy. Reference operators resolving data ranges process before any mathematical operations occur. In this financial formula, the engine resolves the addition within the parentheses first, followed by the exponent, and finally the division. Without parentheses to dictate precedence, the division resolves before the addition, changing the logic of the equation and producing an incorrect result. This is dangerous when discounting cash flows, where a single misplaced operation silently corrupts time value of money calculations. Parentheses act as the primary mechanism for overriding the engine's default mathematical logic. Understanding this internal parsing syntax prevents minor keystroke omissions from becoming catastrophic model failures. The engine also manages decision-making through conditional logic functions. Legacy logic required nesting multiple binary statements inside each other, creating complex formulas that were difficult to audit and easy to break. Modern architecture uses sequential logic gates. The IFS function pushes a data point through a series of tests. It processes from left to right, stopping immediately once it finds a match, ignoring all subsequent tests. This requires including a final catch-all condition to handle data that fails all specific prior tests. This sequential approach creates robust models, significantly easier to maintain than those built with nested logic. Beyond the computational core, the system utilizes pattern recognition to automate data cleaning. Pattern-based algorithms can infer user intent from a few examples to parse or reformat raw text. This results in a static extraction. The output is a one-off transformation that does not update if the original source data changes. For dynamic organization, systems use tools creating collapsible hierarchies based on changes within the dataset. Automated subtotaling requires sorting first. Without it, the grouping logic fractures, creating a new subgroup for every single row change. Proper sorting allows the engine to detect logical transitions, inserting summary metrics at the correct intervals. This spatial discipline also applies to complex querying, where Boolean logic is determined by cell placement. Criteria positioned on the same row execute an AND condition, requiring all parameters to be met. Staggering criteria across different rows executes an OR condition, pulling any record that meets at least one of the requirements. Mastering this enterprise data organization is strictly dictated by understanding this exact combination of precise sorting and physical grid layout. Summarizing massive data sets requires moving beyond standard cell logic to multidimensional aggregation tools. To maintain speed, these tools bypass the standard grid and take a snapshot of the data, storing it in an isolated memory abstraction called the pivot cache. This cache requires strict database hygiene, unique headers, contiguous ranges, and atomic data. A properly structured cache acts as an engine for multiple analytical views and interactive panels. Creating entirely new tables from the same source data can generate redundant memory caches, leading to excessive file sizes and system latency. Copying and pasting existing tables ensures the software shares a single optimized memory cache across all views. This completes the model, moving from spatial referencing and logical parsing to the final layer of memory management. By managing these internal layers, the analyst builds a system capable of handling complex, enterprise-grade business intelligence.